Understanding the time complexity of summing m vectors of length n. Introduction. Summing multiple vectors of length n elementwise is a common problem in linear algebra and programming. However, there is often confusion about its time complexity, whether it should be considered mn, or something else. The problem. Given m vectors, each of length n, the task is to compute their elementwise sum. S equals v underscore 1 plus v underscore 2 plus backslash dots plus v underscore m. How do we analyze the time complexity of this operation? The straightforward complexity analysis. Each vector has n elements, and to sum m vectors elementwise, you effectively perform m1 times n additions, adding vectors 2 at a time across all elements. Therefore, the time complexity is mn. This means the computational effort grows linearly with both the number of vectors and their length. Framing the problem changes complexity. If the vector length n is fixed and small, example, always length 10, then n can be considered a constant. Complexity reduces to m, focusing on how many vectors are summed. Conversely, if the number of vectors m is fixed, the complexity can be n. The choice of what variables you consider as input size influences the big O notation. Impact of hardware and parallelism. In real systems, the wall plot time depends on hardware features. Vectorized SIMD, single instruction, multiple data, instructions or GPUs can process multiple elements simultaneously. This can make the effective runtime closer to m by parallelizing the elementwise additions. Parallel reduction techniques can improve efficiency from mn to roughly n/log m by efficient merging. However, the theoretical complexity remains mn despite these optimizations, since all elements and vectors are ultimately processed. Summary. Summing m vectors of length n requires mn operations. How you define input size variables affects the complexity notation. Hardware parallelism can significantly improve practical performance. Always distinguish between theoretical complexity and real-world execution time. Understanding these distinctions helps clarify why some additions in linear algebra are sometimes treated as constant time and sometimes not. It depends on the problem's context and the computational model considered.